Hello everyone, can you hear me?
Yes.
Very good. I am now recording. Let me know if that is not okay with you. I hope you have seen or at least had received the links for the previous videos. And if you have any comments, just please let me know. Just as much as any comments or requests to questions to the lectures themselves, or any topic that you would like I said earlier. Okay, I will just go ahead and share my screen now. I hope you can see this presentation. All right.
Can it be a bit bolder, like to Zoom or something? Is it possible?
I will see what I can do. This is about what I can do. Do you see the presentation okay now?
Okay, I will try.
Yeah. You will also have the recording, and it's the same presentation as I sent in preparation for this lecture. A bit sorry that I was a little bit late with it. Theoretically, you can actually follow the presentation that I sent you on email. That would probably make it larger for you, as you can put it at any shape that you would like yourself. All right, so today, 17th of February, and we're going to just have a quick look at the overview of the topic of casing design for 2025 in your class, Drilling Engineering 3. Basically, we have covered material science and introduction to well construction, and we're about to start on the essence of casing design, advanced casing design. We will split the topic into two. Again, what we're going to do is lecture the theory, and for the first part here, we're going to look into acting forces and understanding how we do the analysis of casing design, so that you know what to look for and have like an understanding and a gut feeling what this is about. I'm still hanging on to the two topics that were requested last year, P&A and corrosion, hoping to develop them a little bit more compared to last year's lectures. The previous lecture, we typically repeat every lecture just to get into the mode. The topic was introduction to well construction, and we did an overview introduction. We talked about the casing setting depths and the number of casings. To repeat, what we did was to talk about the basic naming of the different casing strings, of course, and the nature of their importance, what will be the key factors per section. What we'll do, we will touch upon that and build upon it more meat on the bones, if you like, as we discuss and go through the different topics listed in the overview, even as we talk about P&A and corrosion topics. We had a video looking into how casing and wellhead is installed. how that works. I hope that was informative for you guys. We talked about the setting depths and the number of casings. They would be typically very strongly connected. If you need to set a casing shallow, typically you would need to add another string or section in order to reach your target. Now the subtopics, casing design, the strength of the tubular themselves and the acting forces, those topics will be discussed over the next lectures. So that will determine the setting depths and number of casing strings, if you like. Other things that influences the number of casing strings and setting depths, as we talked about, we had a really good question about this in the last lecture, and touched upon the topic of kick tolerance, which typically fits under drilling design. Also, we talked about very briefly, and what probably is knowledge that you already have acquired through previous courses, is the drilling window, avoiding kick and avoiding frac. So you need to have a certain window between the pore pressure and the fracture gradient, which typically also is a sub-topic under kick tolerance. Now, what we did not say maybe strongly enough, torque and drag. In order to have a feasible casing setting depth, you need to be able to run and install the casing or liner. If torque and drag is significant in a section, these things are done under the drilling design, not only as a software, but also it's typically what pertains, or what sorts under drilling analysis. Yeah, I put the reach or ERD, extended reach development, as a keyword there, and I presume that you guys have discussed and acquired this information in previous courses. Otherwise, just drop me an email and I can point you in a direction of more information regarding this and how it will influence your setting depth and the number of casings for a well. Now, other things that influences a setting depth and the number of casing would be the well path or formations typically. The wellhead location versus its target could be influenced by, for example, drilling from a domestic area. You would typically acquire land where you put your rig, and you will have to drill until where the target itself is. From anywhere where you're allowed to have a drilling rig placed, and typically where in other places onshore, or for that matter offshore, where flora and fauna, where vegetation is not a problem, if there are preservations like areas that are considered nature reservations, you cannot just set up a rig and start drilling, but there could be targets under these areas that are allowed to reach or drain. Either it would be oil and gas, or what is popular these days, lithium brines for batteries. They are also areas onshore typically. I've not heard about any offshore drilling related to lithium reserves, but onshore is quite popular in combination with, for example, taking out thermal energy in combination. Yeah. So So location of where you are allowed to put your wellhead, your drill pad towards the target will determine your well path. There could also be formations or other obstacles in your way from where you start drilling. Typically, what we have in some fields in offshore Norway, paleosols, this would be formations that easily go on losses, not very competent in some contexts. You need to keep certain inclinations through these ones. You also have the smectites, very extremely reactive shales with a certain time limitation. Say that you drill through it, and then you need to, of course, stop drilling and install your casing or liner as soon as you can. We have a question. Go ahead, please. You're muted, please.
Yeah, not really a question, but prior to the commencement of the lecture, I know you always ask if we have any request or something. If we have any topics in mind, do we have to send you an email? Like, I have some few topics that I don't know if they will be part of this lecture already, or
Yeah, I propose that, well, you can just ask. It's not a problem. If it is part of the lecture, I will let you know, or I can add it. You can just ask now if you feel like it.
yeah, I have like 3 topics in mind, and I don't know if I had them at my university. One is drilling problems. Another one is drill string dynamics.
Yeah.
And maybe something that has to do with new development in drilling operations.
Yeah. I would say that my scope, the scope that well, what the university has scoped me with is a limitation to casing design, and anything that comes or kind of what to say, influences casing design. And I feel that maybe drilling problems is kind of borderline because I am now talking about formations that are kind of giving you drilling problems that leads to a way where you have to mitigate it through your casing program. But there are so many other drilling problems. So, I cannot embark on giving you an overview through these lectures that are set up for casing design to cover others that others than those directly influencing the casing program. I'm sorry about that, but what I can do, I have certain materials that I can send you on an email, links, attachments, so on, where you can find answers to many of these things. Yeah. I hope that answers your question with regards
Thanks
to.
a lot.
Yep.
I will so much appreciate that.
Yep. No, not a problem at all.
Yeah,
Yeah. So
thanks.
yeah, and you could also in some cases, I know that there are some fields that has like a salt dome, or it's actually like a chimney, so the pressure becomes very strange through a salt formation, because it's so vertically yeah what to say. It goes from deep until shallow, cutting through a lot of formations. And if you drill into one of these and you destabilize it, you will have a lot of trouble, meaning that you need to drill around such an area. And there are, of course, in the same nature, other well paths that you need to avoid. These are all obstacles or problem formations that will dictate how your well path and again how the torque and drag will be, and again how your casing program might be influenced. So that's basically direct or indirect what we talked about in the previous lecture. We will now embark on the essence of the 6 lectures that I will give in this class, TPG 4242 at the NTNU. This is chapter 3 of the lectures, or to say it, we will do section design pressure in this lecture, and we will talk about the acting forces and start to understand what load cases are and how to do analysis of this. That's typically what is listed in number 4, design analysis. And we will also touch upon point number 5, regulations. But both point 4 and 5, we will just touch upon them. We will go further in these later on. And the strength of tubulars, we have just touched upon that topic in actually lecture number 1, when we talked about yield as a limitation, because we don't want to deform our pipes to keep drift. That being said, let's just jump right through it. I think I showed this slide as a teaser in the previous lecture, talking about the forces that are acting on casing. And what we will do, we will use the drawing on the right here. This drawing, we will have to do a mental exercise with it, thinking, okay, on one side it clearly looks like it is drilling, but the mental exercise will sometimes it will represent a casing that is either installed or about to be installed, being run in the well. And the things that we will consider in that mental exercise, we will go ahead and think about what collapse forces are, what burst forces are, and axial loads. We will all see what are the acting forces that results in these typical stresses acting on pipes. A list here, internal surface pressure, that's typically what we apply. It could be either operational things like when we are circulating, it could be when we are pressure testing, it could be, for example, cementing. And the same goes for external surface pressures. It could be different scenarios that we're doing. We could in some cases do different density profiles. When we are installing a casing, we are running it inside the previous casing, and that casing has the previous mud or whatever it was that we pumped ahead of the cement. That will be in the annulus of the previous casing. What we will have to consider would be buckling. But when we are running casing in, could it be exposed to forces that are creating buckling or sinusoidal buckling into it, helical or sinusoidal? Again, the internal density profile, what are we pumping ahead? We sometimes are using just, in most cases, using just what we drilled with. In other cases, what happens is that we put in special mud or fluids because we know it's going to stay for a very long time. It could be just additives or chemicals. Regardless, the cement itself would very often have a different density profile than what the drilling mud has. You can drill with anything from 1.03, typically saltwater profile, up until very high densities in HBHD fields. But normally the weight would be typically, say, just to pick a number, 1.2 SGs. And any cement, normal cement, 1.75 SGs, up to extreme cases of 2.0 SGs. So internal and external density profiles during cementing is quite common. And what follows, of course, would be some U-tubing effects while you are pumping cement. What influences us would be casing wear, and typically, since we are doing life cycle analysis, would be corrosion. We have to consider corrosion. In most cases, how we solve that would be to actually add some corrosion inhibitor type chemicals. And confined in the cement or other places, we introduce either actual stress from friction, typically in the bottom part where we are cementing, or the cement itself creates buoyancy effects, and this could be locked into the casing as we are cementing. What we'll learn is that cement, it has one consideration as it is wet. It has one consideration as it is about to set up. And the external pressure profile in cement, what we do is consider the pore pressure outside in the formation. That's kind of following what we call the worst case scenario, and that's what we always do in casing design, thinking worst case scenario. We can just jump on and talk about cement immediately. Cement, when you're pumping it, as said, the density itself has an effect, direct, and that's one situation that we need to do as an analysis. Once it's in the middle phase, and that starts basically 1 hour after pumping, when the cement has been in place for 1 hour, we have pumped it, we have stopped the pumping, and it is in the annulus where it's supposed to be, or where it has to end up because of, call it operational factors, meaning you had maybe some problems and that was not exactly how you planned it, but this is how it has to be for all matters. I hope you understand what I'm talking about. Sometimes we don't bump the plugs. I hope that gives meaning to you. If not, we will have to go and step back and do another, call it introduction, and that will be outside these classes. Sometimes cementing operations doesn't go entirely after plan, but still, one after we have stopped pumping and it is where it ended up, you have to say this is it. What takes place with cement, and I will compare this to sand at the beach. Cement, as you're pumping it, is wet, just like mud. After 1 hour, it starts to set up, and it becomes a little bit like if you have been to the beach and you're seeing sand as it is just in the portion of the beach where the waves are coming in. You can form it like a snowball, the sand, but it doesn't really have any binding. It doesn't bond. It doesn't. It forms to your fingers and your hand, but it doesn't stick. And that's the that's the texture. That's the shape that cement will have from about after 1 hour in place and until it has the final setup. It means that, say that you do something to your well, your casing, say that you start pressuring it up or do operations inside the casing that disturbs the shape of the casing. Either you draw the pressure down or up, or you do something in the annulus. The cement will take the shape as sand does in your hands, like a snowball, and it doesn't go back. It does not form the void anymore. So the bond between the casing and the formation will not be perfect anymore. That's why we have operations that sometimes say wait on cement, because having the bond between the casing and the formation is extremely important for integrity. We say that in the phase between 1 hour after pumping in place until it has been fully set up and built its yield strength, we say that the cement, it is not a liquid anymore, and it's not entirely a solid. So we give it a density profile of 1.0 SGs. That's what we say in casing design. After it has set up, it is a solid, but just as a shale has the pore volume and permeability as a red brick, and cement will have the same nature, the same properties as a red brick, theoretically, or shale. We say that it has porosity, we say that it has permeability, just extremely low. That's why we give cement, once it has set up, the same pore pressure as the formation that it is kind of sealing. A worst case scenario treatment. All right, we are changing the topic now and looking into the acting forces. What gives us collapse, burst, axial forces, and what is actually the physical case in more or less absolutely all scenarios. a combination of them, which we call triaxial. What we see on the right is a triaxial analysis plot. This you saw earlier. We call it the von Mises plot. The red oval or circular shape is called von Mises plot, and the vertical is pressure and the horizontal is the type of stress, axial stress. It's basically just an orthogonal plot inside the von Mises equation, which forms that red circle. We have quadrants, and Q1 is where we have a positive internal pressure of the pipe, and we have tension in the pipe. Quadrant 2, that's where we have compression in the pipe and positive internal pressure, calling that normally burst pressures, when the internal pressures are dominant. And in quadrant number 3, still compressive forces in the pipe itself, but now the forces externally, the pressures externally, are the dominant ones. Going on to quadrant number 4, here is where we have tension, stretch in the pipe, and at the same time the pressures externally are the dominant ones. What seems to be, and that's just an optical illusion in a way, how to explain, these segments are actually just as big. The area in Q1, Q4, Q2, and Q3, they're actually the same. It doesn't look like it on this plot, but the truth is, mathematically, looking very much into details, they are basically the same. It's just a mathematical consideration. It doesn't mean anything for us. It's just an analysis, and we're stepping into the first understanding of how does this pipe hanging from the rig, either it being a drill string or a casing or a liner on a piece of pipe, drill pipe, how it works and how to consider these 4 different stresses listed. Let's look at point A and point B on this hanging pipe. And we can look at them with or without pumping or pressure testing. In our triaxial plot, this is how it will look. Just basically with no pressure, we see that the pressure is 0. The stress is the highest in the pipe where it's hanging from the rig. That's where the tension is the highest. And the stress level is the highest. Going down to in the well, the tension is reduced a lot, and we see that in point B. Now, if we add pumping or pressure testing, that's going to change the location in our triaxial plot. The pumping pressure is higher in point A because it has more friction than point B. If it's pressure testing, it's going to be a little bit different because point B has the additive of the fluid column. So then it will be reversed. The pressure will be higher at point B. But as a triaxial plot, there's more stress in point A regardless. Now this is a pressure test externally. Say that you are pressure testing in the annulus. This is how it would look. Meaning, the density profiles would of course give it. I have to push it a little bit up, I guess. Something like this, to show that there's a higher density, so the differential is different. All right. Sorry, I was wrong. This was internal. It says external there, but it should say internal. So I'm confusing myself, and then it would be this plot. If it's internal, then it should be. Let me see. This one is we just delete it. This is how it should be. Yeah, external. That's how it should be. Density difference. Sorry about that. Let's go to point C. Point C is an interesting point because it has zero axial tension. It's the neutral point of the string. It is here plotted with pumping, meaning that it has some internal pressure. Now, below the neutral point, we will find a place of compression. If we are pumping, it would be in quadrant 2. Now, all what this is leading up to, all these reflections that we've been putting together, that is to entertain this picture, what we call the load cases. And these cases, these scenarios that occur during the lifetime of a well is kind of standardized. You'll find a few of them in the NORSOK standard D10. You'll find more in other standards. What is listing here is typically what you'll find in an operator's governing documentation. So here are more load cases than what would be in the NORSOK D10 standard. And typically what you need to do as a drilling engineer, doing analysis of casing, liner, tiebacks, and tubing. Now, up to the right is a software analysis using the different load cases. I'm sorry that the picture up there is very small. Let me see what I can do just briefly for you guys here. Now you should see the load cases better. So initial conditions are very, very important. That's say what state was the tubular that we're doing analysis on, what were they basically at temperature-wise, densities on the different sides of it, any torque inside, or maybe not torque, but say friction and bending and so on. These things are important. So initial conditions, well, in software, it typically comes down to temperatures. That's what it does. And what we're talking about frac, that would be a scenario where you are fracturing the formation, bullheading heavy fluid at high pressures. This is a pressure test with a certain fluid gradient. This is something called green cement test. Drill ahead, blah, blah, blah. Many different load cases are listed here, including taking a kick, annular pressure build up. That is a production load where we start to produce the well, and typically the annulus fluid heats up and creates thermal expansion and pressures. The different load cases listed here, all of these ones are purely what we call drilling loads. Drilling loads, they are not really limiting or determining our casing as per se, and call it these scenarios here are not the ones that set or determine the grade or thickness of our casings. In many cases, these are more lenient than what we call the production load cases. And they are here. The production load cases typically determine what kind of what type of weights that will be used, and the grades, what yield we are going for in our casing strings. And we see the list here on the conductors, what kind of load cases they are subjected to. We see typically surface casing, drilling liners casings, and tiebacks, what kind of load cases they are subjected to. Production casings, anything call it a production annulus exposed. It could be a liner, it could be a tieback. And I'll show you a special scenario before we hang up. And the tubing. Tubing would always be the one string that is exposed to the highest loads. And production casing liners typically would be designed to the same, unless it's something special, like a frac. That could be different. I promised you a special case. If you look at this well here, it has a production packer here. The special case is when, say, that you have a production liner. Then there will be two sections that are called production casing liner. I'll explain better. Say that you have a 9/5/8 inch section, and then you have to drill an 8.5 inch hole down to the top of the reservoir, and you install a 7-inch liner. And then you start drilling a 6-inch hole through the reservoir. Then in the situation where you're drilling through your reservoir, the 6-inch hole, you will have a 7-inch liner and a 9/5/8 inch casing exposed. Both of them would be regarded production casing liner, and they will all fit into this category here of production loads. Here, the drilling loads for the same. And with that, I think we take a break, unless you guys have a question. I'll just say sorry about the extra slide that snuck in there and confused me. I hope it didn't confuse you guys. These cases that we talked about, they are in principle very basic and simple. And yeah, I hope I didn't confuse you with that extra slide like it confused me. Thanks. All right, back again after the break. No questions, so I hope that it was clear, even though I stuttered a little bit on that extra slide that was not intended to be there. Let's talk more about the load cases. That's why I put in those, call it simple analysis that you can actually redo for yourself and see later. Since you have a copy of the presentation, you can do that in peace for yourself later. The load cases, they are the essence. They are predefined in most operators governing documentations, and we will have a separate session on governing documentation later on, because it's well, as you will see later on, there are things there that pertains to casing design. It's a lot about integrity, and that's why governing documentation has to be part of these 6 lectures that we do. The load cases. Top here, first one listed, displacement to gas. It means, and it's a situation where the casing that you have installed and you're drilling, a situation where the whole casing is displaced to gas. This is an extreme case, and yes, it's not very, very likely to take place, but still it's a scenario, and it's call it a design philosophy more than a probable situation. What we do is design the casing to be stronger than the formation below its shoe, meaning that what should break is basically the formation under, and not the casing. Even with full displacement to gas, the casing should be okay and not affected when the fracturing gradient is gone. Any pressure test that is required, of course, should be investigated and designed, and the casing should be designed to take the pressure test. The pressure test, the philosophy behind the pressure test, basically it's during or part of the casing design where we are developing the pressure tests. We do all our analysis and see what are the different loads. We can again have a quick look at the inserted plot up to the right. We see where all the different pressures are going. Let's have a quick look again. Typically the yellow line, that's the collapse pressure. It doesn't say pressure test in blue here. External pressure. So basically what we do is to design so that a pressure test that we're doing should be the highest load any part of our casing see. Pressure testing is basically certifying the casing for use. So that's how we design our pressure test during the casing design process. Green cement test. That is basically just the same as the pressure test, only it is done within the hour before the cement goes into the second mode, where it is having this intermediate phase, like discussed in the previous session. So you pressure test most cases just as you bump the cement plug. Then you continue to let the pressure go up to the level of the pressure test that I have identified through your casing design analysis. Drill ahead is a situation where you are basically just checking what are the loads going on as you are drilling out of your cemented casing and starting to drill the section. Say that you have a very, very low drilling mud that you're using, and the previous section was very, very high. Then the installed casing that you're drilling through will have like a collapse load from the different densities. At the same time, it could be other situations that are planned during the drilling. So all of these things needs to be investigated. The drill ahead is basically to cover anything taking place during the operations of drilling. Cementing, I think we talked about that part in the previous session of this lecture number 3, meaning that the cementing is different density than mud very often, and you're pumping it through your casing, and then it goes into the annulus. You're bumping your plug. It is a liquid within the first hour, then it turns into 1 SG, and then it sets up, and then it turns into a very low permeable, but still not impermeable solid. And of course, that is in regards to casing design and the philosophy that we're using in casing design. Yeah, it is so slow, the permeability that we say for all in well integrity perspective that it is impermeable. Lost returns with mud drop. That is a load case where we are simulating that we are having total losses. And the drilling mud will drop until the column of mud that remains in the well balances the pore pressure, not the fracture gradient, but the pore pressure. Very special and kind of improbable again, but this is again a casing design philosophy. Next load case is called run in hold. Basically, this is a situation where we are doing torque and drag analysis, and it's not done in any casing design software, but a drilling design software in most cases. And just since you guys are about to become drilling engineers, you will have to get used to the fact that most of the support that you will get from service companies like those providing directional drilling services, they do not do torque and drag for casings or liners. They only do with their drilling scopes, and they consider cement installation of casing and cementing as their, call it, break before they again have to go and drill. That's my experience. So you will have to get used to actually running torque and drag for casing, liners, and so on, tiebacks yourself. Yeah, just some experience transfer for you guys. Overpull. Okay, so in your governing documentation, your company would say, okay, we're struggling sometimes to install pipes. Very normal. It happens every now and again, especially if you're drilling difficult holes and formations. What's going to take place is that you need to be able, with the top drive and the setup of the pulleys, that you can make a certain amount of overpull over the hanging weight of your casing, tubing, liner, whatever it is. So in some cases it says, for some companies, that the minimum capacity over the hanging load should be 100 tons, for example, metric tons. It could be different. It could be different numbers. This is just so that you guys understand what it is. Again, this would be tied back to a drilling software and part of the torque and drag situation. And post cementic static load, you just have to understand what is the number before and after cementing. Casing evacuation, that is a situation where you are doing what we call gas lift. That's a gas lift casing or load case. For casings that are typically in the A annulus production casing, with say a gas lift valve through into the tubing, and in that case you will have like an evacuation situation where on one side you have potentially a leak, so that the gas in the gas lift is the pressure is not sustained. It goes down to say 1 bar. And then whatever fluid, and on top of the fluid, any pressure that is in the B annulus will act as, for example, a collapse load on the casing, the intermediate casing it would be, or yeah. It depends on the casing configuration, but you get the point. It's an analysis that you will do considering gas lift. Production loads. We will go in detail through tubing leak. It is basically what it says. Say that your tubing develops a leak, then the pressure inside the tubing will flow over to your A annulus. And in addition to anything else that is there, you will have the reservoir pressure, shut-in reservoir pressure on top in the A annulus, on top of everything else. And in principle, that's why we say that we have to design the production tubulars to the same level as the tubing. Cleanup, that's the first flowing of the well. We have to then consider whatever it is of fluids inside the well and the reservoir pressure in initial pressures. Could be anything inside, could be brine or mud when you start, and yeah. So basically this is to cover all bases, and any scenario that the well goes through, all tubulars needs to be certified that they can tolerate absolutely any of these, call it extreme cases. and situations, any situation that the tubulars will see. And the first flowing of the well, like said, initial conditions. Anything that happens during well construction is pumping fluids from the surface and down. And this fluid will very often be considered cold. So you're kind of cooling down the well and the tubulars. Once you cement and you lock in the bottom part of a casing, then it's tied to and glued to the formation there, locked, and as much in the casing hanger is locked into the wellhead, meaning that the pipe is strung up in both ends, locked in both ends. So anything that happens of difference in temperatures from the cooling down of the surface fluids during pumping, including cementing, that heating up of the that takes place when you start producing the reservoir fluids is gonna be a change in the tension. Early life production, the difference between the first cleanup and the early life production would typically be the densities. And then midlife production, the difference over from early life production to midlife would be the reservoir pressures. Late life production, the absolute potentially depleted part, or in some cases it could be gas breakthrough, so very low pressures combined with very low densities. All of these things needs to be considered. And yes, we are going again through worst case scenarios with the lowest pressure support in the annulus and the highest pressure on the inside, and vice versa. The highest pressure in the annulus and the absolute lowest pressures thinkable on the inside of the tubulars. And I will repeat, it sounds very extensive and exhaustive, but it is the list that you see here on the previous slide and this slide, the drilling loads, and now we're going through the production loads. It all boils down to these ones. Let's just cover shut-in, and that's when you're closing in the well after you just warmed it up, I guess you can say would be the worst case, and then a short shut-in and then a long shut-in. These things, they are not really it's the cooling off that they are after in the difference. It has to be a very special well and a special situation to make these load cases impact the type of tubulars that you're selecting. Annulus active, that is again covering two situations. Cuttings re-injection, cuttings injection, grinding up the cuttings of oil-based wetted cuttings and slurrifying them and then pumping them into any formation that can receive this type of fluids. Bullheading, that's typically what we do in interventions. Say that you want to do some scale inhibitor treatments, then you need to be able to bullhead. Typically what takes place there would be that you are below the fracture gradient, so you're using the permeability of the formation. You stay below frac. Kill operations, those could be theoretically above frac, but They are governed again in governing documentation. Your company will tell you what figure to use for the different strings. It doesn't really say here in the directly, it doesn't say, but we will get back to it. It's covered in displacement to gas actually, and we will discuss why, because it ties into what we call the section design pressure. Everything will become clear in few minutes in this regard. Let me see. We are in kill operations, stimulations, mini frac. Yeah, then that's a mini frac is very often either yeah, call it an extensive leak-off test. Mini fracs, they are typically used as data input for a fracturing operation. In those cases, you pump, say, 5 cubic meters of fluid into the formation after you have broken it down. Say that you see the leak-off point is clearly indicated on your volume pressure graph. Then you pump another 5 cubic meters to see how frac propagation works. Yeah, breakdown that is covered. It's just it's yeah. So that's the mini frac pumping the 5 cubics after leak off point. Yeah. All right. We are going into an example looking into what these different load cases are. Not every one of them. We will take one and do quite an analysis of that one. And for the other ones, you will you will have to investigate for yourself. You will, I'm certain, as drilling engineers, learn details about each and single one of them. I'd say that this load case called tubing leak, this is one of the probably the most important in many cases and contexts. This is probably the most important load case because this is the one that determines, in most cases, what kind of casing you need to have when it comes to yield and thickness for the production casing. Yeah. For the other casings, very often it's displacement to gas, and as I promised earlier, we will go through that load case in parts later. For now, let's look at the tubing, how it is influenced by tubing leak. All right, what we see will be the graphs of the different acting pressures. We see the reservoir pressure down to the right in golden, and it goes up. And then as it hits our tubing tailpipe, the part that goes into the liner, it becomes stapled. If we go a little bit higher, we see where the production packer is sitting, and at that point in time, in that place, we go to the right and we get a blue line, and that's the annulus of the tubing. In the annulus of the tubing, we have the packer fluid, and the packer fluid gradient is much more aggressive than the internal gradient of the tubing that is stapled. In red, we see the difference between the internal stapled golden curve and the blue one in the annulus. So if we go from the bottom again at the tailpipe, it will be no differential pressure over the tailpipe, because the pressure in the annulus or pocket between the tailpipe of the tubing and the casing needs to be the same as inside the tubing itself. I'll explain. That is well construction, and it ties into casing design. There are two things to consider. One, and that's quite quick, that's corrosion. We have a different material quality in the tailpipe in the whole in the whole of the tubing. It will in most cases be a 13% chrome material, whereas in the casing it will be a lenient low carbon steel type casing. And still there will be formation fluids in the pocket that we're talking about between the production casing and the tailpipe of the tubing. How corrosion actually works in this case, all the fluids that over time is produced, they kind of leak over through the connection between the liner hanger and the end of the tubing tailpipe, because you need to have at least a one-way communication there, going from what we call the initial condition until we heat up through production. The pocket will increase in temperature, and what we will have is an annular pressure buildup. As a rule of thumb, what we're using in the field is that we say for every degree that we heat up, there will be 1 bar increase. As we are say that we have 50 to 70 degrees Celsius down there as initial conditions, and we can have as much as 120 to 150 degrees depending on how deep the reservoir is. Increase it will then increase the temperature of say 70 degrees. That means that the pressure in that pocket will increase 70 bar. We cannot have a situation where the pressure increases like that in that pocket. So we need to have like a one-way seal at the stinger going into the liner hanger, or a fully open two-way communication. Doesn't really matter. The fluids from the reservoir that goes into that pocket, all the corrosive elements, they will be spent. And it's not a lot of liquid there, and the corrosiveness of the reservoir fluids, it is tied to the fact that you are getting new fluid all the time over a very long period. Then it becomes corrosive. You can have some reservoirs that are extremely corrosive. Those would typically be high CO2 or high H2S reservoirs. Then you have special material qualities, and those are special cases, I'd say. in most cases, you have just few and low partial pressures of these components, meaning that the little fraction doesn't really even influence the carbon steel there because it's a dead leg. Once you shift out, the pressure is the same and you don't really have any replacement. So the corrosion will take place in the tubing because it's seeing new fluid all the time, whereas you choose a corrosive resistant material like 13% chrome there. So corrosive resistant tubing, and you don't really need corrosion resistant casing because the fluid is not gonna be replaced. It's a dead leg. And it has the same pressure. All right, over the production packer, we will have quite a different pressure going from below until above. So the difference between the internal and the external, we'll see that the pressure is higher in the annulus than in the tubing itself. So it's a compressive strength, a collapse pressure. And the collapse pressure, it goes on all the way up until it crosses the black line, which is said to be the zero or pressure equilibrium. And that takes place, and it's random in this case where this takes place. It's purely from the selected gradient of the reservoir fluids, from the reservoir pressure, and the gradient of the annulus. So it's in this case just below the marked downhole tubing hanger. Yeah, so that's where the differential pressure goes in this situation. And this is taking place before the tubing leak. Now, the most extreme case for us in the tubing leak would be a shallow leak, meaning just below the tubing hanger. It's marked here with a white circle. Now we have a leak, and the difference basically is that the packer fluid gradient will have to start at where the tubing internal pressure is, because the pressure, the shut-in tubing pressure, is the same also in the annulus. So now the external pressure gradient, it goes from where the internal tubing pressure or shutting tubing pressure goes and out. So we have a much higher pressure in the annulus now. We have the shut-in tubing pressure plus the gradient going down. The internal pressure of the tubing would remain the same, and the difference, the tubing, the differential pressure over the tubing before the leak and after the leak, we see the difference here. The differential pressure is much higher, and this is for the tubing a collapse load. We see now that the collapse force has increased a lot. So this is in a way giving the limit of the collapse force of the tubing. Not necessarily the highest collapse force that it will see through its lifetime. That needs to be simulated. But in many cases, it is. All right, so this covers the load case tubing leak for the tubing. It is a collapse load for the tubing. We will now quickly touch upon tubing leak, how it works for the production casing. For the production casing, it is a burst load. So inside the tubing, we have the regular golden stapled line. We have the internal annulus packer fluid gradient, and you have some fluid in the annulus of the production casing. And in red, we see the differential pressure between the green external fluid. Because it's cemented, it should be vertical, meaning it's like the formation pressure there, and which we don't know for this case. And it is the drilling fluid or whatever fluid that is on top of the cement in green. Once the leak occurs, we will have the extreme pressure on top of the packer fluid going, just as we said for the tubing. The support on the outside of the production casing will remain the same. We all see that we see that the differential pressure has shifted. It is now higher on the positive side, meaning that this will be an increased internal pressure of the production casing. It's a burst load. So tubing leak is a collapse load for the tubing, and it is a burst load for the production casing. We don't have much time to cover the section design pressure. This is the highest load that any casing or liner normally see through the lifetime of the well, except for the production casing or any casing that sees cuttings injection. But it needs to be detailed in analysis. But in most cases, this is the highest load that we normally see. What we say about the section design pressure, it should cover the absolute highest. Maybe I was talking around myself a little bit. I was thinking about actually the displacement to gas. So maybe I was actually wrong. I need to say that again, so I'm not confusing you guys. Maybe I confused myself there again. Sorry about that. Displacement to gas. That may not be the highest load that we see. We may go through other situations and see load cases and see that yes, we are covering the highest load. Section design pressure should be the highest pressure that any of the casing strings see through their lifetime. So what does this section design pressure actually mean for us? In operations, it means that before you drill out the casing, you need to pressure test it to this level. That this pressure test is what we certify the casing with, saying yes, it's good enough for the life cycle of the well. So this pressure test is extremely important. It comes from displacement to gas in most cases, or as we just saw, tubing leak for the production casing would often be the case. I was a little bit confusing myself, I think, saying that section design pressure, it's a combination of anything along the string. It needs to be so high, this section design pressure, that it goes beyond any of these curves, any load. So a pressure test will have to go on the outside of the yellow curve for an external pressure, and if it was these loads were internally, it needs to also exceed the internal pressures, if you see what I mean. It has to be the absolute highest load that the pipe see through its life cycle. So we take care of in the section design pressure the certification of the pipe. Some examples here of where we can find the highest loads. And in most cases, except production casing, that this would be the displacement to gas. As I indicated earlier, we have for killing, we have input from governing documentation. In casings or liners larger than 6 3/4 inch, we say that we add 15 bars. So say that a gas-filled casing will give you 100 bar as the maximum possible shut-in wellhead pressure. You add 15 bars and say, this is my section design pressure. For casings smaller, you add 35 bar. And it's the same for intermediate and production casings. 35 bars you add. And these are all, this would be to be able to kill the well. Yeah. Calculation example, just to show how this works. The fracturing gradient below this casing shoe is set to 1.5 and the depth is 1050 meters. We always assume some 0.15 SGs for the gas itself. And that amounts to, through our calculations, to 154 bar. Pressure. What we need to do is subtract the weight of the column of the gas, correct for it, so it's 15.5 bar. So the fracture gradient is 154.5 bars, and the wellhead pressure would be subtracted the 15.4. So the maximum pressure you can see on top would be 139 bars. 139 bars is not possible to have a higher pressure than that for one of these shallow casings. And since this is a large casing, we call this in the software where you're doing this analysis, it's called limit to frac at shoe principle, like we talked about earlier. Now, this 139 bars, we add 15 bars because it's a large casing, larger than 16 3/4 inch. We add 15 bars. And then the section design pressure becomes 154 bars. In advanced casing design, where you consider cuttings reinjection and so on and so forth, then you could run other load cases. In most cases, it wouldn't be higher than this. This is where you, to put it straight for you guys, this is the pressure you are bumping the plug with, or the green cement test for that matter. So when this casing was cemented, you would see a 139 bar pressure test when you bumped the cement plug, or through the green cement test. If something happened and you didn't bump the plug and you waited for the cement, before you drill out of the shoe, you would do a pressure test to 139 bars. And to your knowledge, the company that provides the rig services, your drilling operator, they would ask you, what is our BOP test? What should I test my BOP to? Your answer is the section design pressure, 154 bars. Yeah. All right. I hope that was clear. There is one point here. If you check what the pore pressure is at the bottom of the section, you'll find that it could give you a maximum pressure of 242 bars approximately, and a gas bubble theoretically could do some damage there. But what happens is that you will get a small frac at the shoe. It's not going to be a problem as per se. Why? Because we detect kicks and we circulate them out, and you will never ever see this pressure on the surface. You will never really go above the 139 bars in any cases. The 154 bars, understand that this is the section design pressure. It comes from being able to bullhead back on top of the 139 bars. That is the philosophy of this thinking, this load case, and the section design pressure, which will be typically an exam question, and it is, I guess, in your exercise coming. We'll talk more about the load cases later and probably do a web exercise. I hope I didn't confuse you guys with my two exchanges there. Please let me know if anything is unclear, if you guys are having questions or anything else. I'm sorry about the 2 minutes overtime. It was just to round off at a natural point in the presentation. Thank you for your time, and see you on Thursday.